So let me start our third day of the conference with a section on topological excitation, where Professor Matsunaga of Tokyo University will present his talk and we'll open our today's session. Please, Professor.
So thank you for introduction. Can you hear me?
We hear you, don't see your slide. Okay, we still.
Can you see my slide?
Yes.
Okay, so thank you for introduction. So I am Ryusuke Matsunaga from the ISSP in the University of Tokyo. So first of all, I'd like to thank organizers for inviting me to this nice conference. So today I will talk about our recent study of the non-equilibrium dynamics of broadband response function in Dirac semimetal cadmium arsenide studied by multiterahertz spectroscopy. So this is acknowledgement to our collaborators. So the spectroscopy was performed by our group members, Kanda-kun and Murotani-kun and Matsuda-kun. And the theoretical part was supported by Murotani-kun and Ikeda-san in ISSP. Then high quality samples was provided by Professor Suzanne Stemmer group in the UC Santa Barbara. And this project has started as a collaboration with Professor Peter Armitage group in the Johns Hopkins University. And I would like to thank all the collaborators. So the topological semimetals have attracted much attention in recent condensed matter physics. So Dirac semimetals has a linear massless dispersion of electron, which can be viewed as three-dimensional analog of graphene. And while semimetals with broken inversion symmetry or time reversal symmetry is also highly interesting material. So optical properties of these topological semimetals are very important because they show novel functionalities related to the linear dispersion and Berry curvature. Then such a novel functionality can appear macroscopically in their large interaction volume with light in the bulk solid systems. Then recently, we have reported the terahertz nonlinearity in the Dirac semimetal cadmium arsenide. So by applying several kilovolt percentage terahertz field inside the Dirac semimetals, we clearly observe the strong third harmonic generation signals in the non-perturbative regime. So it can be detectable on the tabletop light source at room temperature. So this large nonlinearity originates from the intraband acceleration of electron across the Dirac node. Then our experiment demonstrates extremely efficient frequency conversion in terahertz frequency, which may be utilized in high-speed electronics. So similar experiment was also reported as observation up to the 7th order high harmonics, and the calculation for the extreme efficiency has been also reported. So this sample, cadmium arsenide, is a representative material of the 3D Dirac semimetals. So first, the RPS experiment have directly observed large linear dispersion of electron in the large energy scale of 1 electron volt. But the result of the DFT calculation and scanning tunneling microscopy and magnet optical spectroscopy have shown that the Dirac cone in cadmium arsenide are limited in much smaller energy scale of a few tens of milli-electron volt. So this large discrepancy can be explained by the Kane model with the band inversion. So the 2 Dirac node appears in the small energy scale, and there is another large 3-dimensional linear-like dispersion in the large energy scale. So it can be described by the Kane-Bodnar model. So this peculiar band structure makes cadmium arsenide show novel functionalities related to the large linear dispersion of electron. So the infrared response of the Dirac or Kane semimetals have been interested in the infrared optoelectronics and nonlinear optics. For example, such as ultra broadband fast photodetector or saturable absorber for pulsed laser emission, or perfect absorber or stimulated emission and lasing. So to obtain the deep understanding of these functionalities, ultrafast response in the photoexcited Dirac or Kane semimetals is very important. So this figure shows the absorption spectrum in the cadmium arsenide at the room temperature. So the diluted type absorption appears in the low energy side, and the interband transition occurs above 20 terahertz. So the interplay between the intraband free carrier response and interband transition is very essential for the properties of Dirac semimetals. So to reveal the non-equilibrium dynamics, the broadband spectroscopy is very important in this frequency range from the 10 to the several tens of terahertz. So this frequency range from 10 to several tens of terahertz is the intermediate region between typical terahertz spectroscopy and mid-infrared. So it is recently called multi-terahertz frequency, and there have been some important progresses for light source technology. So we have also developed a highly stable multi-terahertz pulse light source, and we developed a multi-terahertz time domain spectroscopy system, which realizes precise detection of the complex response function in this broad frequency window from 10 to 50 terahertz. Here we show the ultrafast dynamics in the photoexcited cadmium arsenide thin film. So we use the near-infrared pump pulse at the 2 micrometer. So this pump pulse excites the carriers, and the multi-terahertz pulses probe the broadband response function as complex quantities with the time resolution of 28 femtosecond. So this figure shows the time-resolved differential conductivity spectrum for each delay time. So the green shaded area corresponds to the timing of the pump pulse irradiation. So right after the pump, the induced absorption peak appears very broadly, then it gradually concentrates into the lower energy side to form the Drude response. So it occurs with the time scale of 0.5 picosecond. So simultaneously, the Pauli blocking of the interband transition also appears as a negative signal of the absorption spectrum. Here we also plot the loss function spectrum, which shows the peak of the longitudinal plasma oscillation. So before the pump, the plasmon peak of the originally doped electron appears at 10 terahertz. Then right after the pump, the peak is significantly deformed and spread into higher energy side. And finally, a single new peak is developed at 20 terahertz. So this result indicates that the photo-excited electrons are summarized with the originally doped electron to form a single summarized electron gas with a well-defined collective plasmon mode. So our observation directly proves that the summarization dynamics on a time scale of 0.5 picosecond. So this is a result of the weak excitation with the expected electron temperature of 330 Kelvin. So the right figure shows the result in much stronger excitation with electron temperature is about 700 Kelvin. In such strong excitation condition, the loss function peak appears in a much higher frequency because the carrier density increases. Then the spectrum is significantly broadened, indicating that the scattering is enhanced between the high density carriers. Then accordingly, we can also find that the well-defined peak appears faster than that in the weak excitation condition. So it means that the summarization is facilitated by the enhanced scattering. So our broadband spectroscopy clarified the full information of the non-equilibrium dynamics in the photo-excited Dirac semimetals. So we also investigated the dynamics of the response function after the summarization. So this figure shows the time evolution of the transmittance and permittivity and refractive index and the co-extinction coefficient. So today we skip the details, but in this experiment, we directly observed that the drastic suppression of the refractive index in the photoexcited Dirac semimetals. The photoexcitation increased the carrier density, and it can also increase the plasma frequency. So then it drastically suppresses the refractive index in the multi-terahertz frequency. So this property may be utilized for the active control for infrared metamaterials. But of course, such a reduction of the infrared refractive index by photoexcitation is a very general phenomenon in any photoexcited semiconductors. The important point here is that the decrease of the refractive index occurs in the energy of the interband transition in these gapless semimetals. So it is closely related to the very interesting light-matter interaction as I will next introduce. So this is related to the coherent light-matter coupling. So recently, the periodic driving of a material in time has been interested in terms of the Floquet engineering. such a time periodic driving can change the material properties by creating the Floquet state in the energy space. So the Floquet state has been directly observed by time-resolved RPS, and many theoretical studies have been reported so far. But there are still lacking the experimental studies directly related for the Floquet engineering. So even a very simple question, such as how can we observe the Floquet state in optical spectroscopy, or how does the response function changes in the coherent light matter coupling, is still not fully resolved. So we investigated the broadband response function of cadmium arsenide during the periodic driving by light. So this is a schematic of our experimental setup. The pump pulse is a narrow band and centered at 30 terahertz with linear polarization. Then this figure shows the black curve in this figure shows that the absorption spectrum of the interval transition in equilibrium condition. Then this two-dimensional plot shows the absorption spectrum as a function of the frequency and pump delay time. So we can find that the spectrum is strongly modified by the pump irradiation. Then the same data are also plotted here. So this figure shows the pump power spectrum at 30 terahertz. Then this is a conductivity spectrum. Then so the conductivity spectrum changes like this in time. So at a slightly higher frequency, the sharp breaching occurs. Breaching occurs very sharply, and the negative conductivity appears as an evidence of the stimulated emission. Then on the other hand, at the lower frequency side, strong absorption peak also appears. So we discovered that very sharp dispersive spectrum appears during the pump irradiation. So here we compare our observation with the case of a photoexcited semiconductor. So when the interval transition occurs in the gallium arsenide, the dispersive spectrum has been reported in the transient transmission spectrum. Then in this case, the breaching appears in the lower energy side, and then the induced absorption appears in the higher energy side. So this result can be reasonably explained by the many-body interaction of the exotonic effect in gallium arsenide. So compared with this, our observation in cadmium arsenide is totally opposite, which means that the breaching occurs in the higher energy side, and induced absorption appears in the lower energy side. In addition, the recent calculation also showed that the exotonic interaction is very small in cadmium arsenide. So the origin of our observation is very different from the case of gallium arsenide. So here we also performed the same experiment with changing the pump fluence and the pump bandwidths. The height of the peaks is proportional to the pump fluence in the weak excitation limit. So it suggests that it is a third-order nonlinear response. But the frequency of the peak and the dip are independent of the pump fluence. Then on the other hand, when we change the bandwidth of the pump, the peak frequency changes and the dispersive spectrum becomes very sharp. So the spectral shape is only determined by the bandwidth of the pump. So we found that this result can be explained by the coherent light matter interaction. Such a coherent light matter interaction is well known in the simplest case of a two-level system. So the incident light creates the Floquet state, and the interaction with the bare electron state makes the photon dressed state. So in this case, the AC Stark shift of the absorption peaks is a very famous phenomenon. But there is another nonlinear response called the stimulated Rayleigh scattering. It resonates between the photon dressed states. So usually the stimulated Rayleigh scattering is not dominant in such a discrete energy systems. But we found that it can be dominant in our case because the stimulated Rayleigh scattering is proportional to the change of the refractive index. So in our case of the solid with continuous band, the pump irradiation modifies the density of states like this into the Floquet. This is a Floquet picture. So in addition, the electron-hole pair density increases by light, so which increases the plasma frequency and therefore largely suppress the refractive index around the plasma frequency. So in such a case, the nonlinear response can be dominated by the stimulated Rayleigh scattering. So in the phenomenological models, the time evolution of the differential refractive index can be written like this. So here I is the intensity of light. So now we detect the pump flow signals, so which includes the transient grating effect originating from the interference of the E pump star and E probe. So please note that the transient grating is usually used to detect the four-wave mixing signals, but the stimulated Rayleigh scattering is different from the four-wave mixing, and the four-wave mixing was excluded in the geometry of our experimental setup. So the stimulated Rayleigh scattering appears in a part of the pump flow signals. Then the nonlinear polarization can be written like this. Then the calculation of the differential conductivity spectrum successfully reproduces the dispersive spectrum observed in our experiment. So we also examined this response in the microscopic calculation based on the realistic band structure of cadmium arsenide. So the band structure can be described by the Kane model with a small effective mass and 2 Dirac nodes. The result of the calculation reasonably reproduces the dispersive spectrum in the experimental result. So importantly, the dispersive spectrum is accounted for by the contribution of the diamagnetic current. So the diamagnetic current originates from the non-zero parabolicity in the band structure. So it means that the stimulated Rayleigh scattering is not specific to the Dirac or Kane semimetals, and it can be found in more general materials when it is coherently coupled with light. The important point is that it can be dominant when the refractive index is largely suppressed, which can be assisted by the plasmon resonance in the solid systems. So, of course, there is a link between the microscopic model and the phenomenological models. So, starting from the microscopic equation of motion, the time evolution of the electron-hole pair density can be obtained as a function of the pump fluence. Then, the diamagnetic current gives the relation of the refractive index and the electron-hole pair density. So, by combining these equations, we can reproduce the phenomenological description of the stimulated Rayleigh scattering. So by using the stimulated Rayleigh scattering, we introduce an interesting aspect of the nonlinear optics. It is called the slow light generation. The speed of light wave packets in materials can be written like this. So it means that the light speed can be drastically slowed down if the dispersion is very large. So such a slow light generation has been widely investigated using ultra-cold atoms, or hyperfine structure in doped insulators, or metamaterials, or photonic crystals. So it is important because it can be utilized for the quantum optical information or sensing. So in the stimulated Rayleigh scattering in our experiment, the dispersive spectrum can appear depending on the bandwidth of the pump. Then it shows a very large group refractive index. So in this yellow shaded region, the absorption becomes almost zero, and the group refractive index is as large as 300. So it means that the non-dissipative slow light can be generated by irradiating the infrared light on semi-metal at room temperature. So, and much slower light can be also possible by using the narrower band pump, such as CO2 laser. So, this result may open a new avenue for the slow light science. So, in previous experiments, the pump light is linearly polarized. But for the theoretical point of view, more interesting situation is under circularly polarized light. So 2D Dirac system can be controlled into the Floquet topological insulator, and the light-induced anomalous Hall effect has been observed in a recent experiment. Then in the case of three-dimensional Dirac systems, the Dirac node can be split to a pair of wire nodes. It has been predicted by theory. So we conducted the time-resolved experiment with a pump of the 33 terahertz circularly polarized pulse. Then as a probe, we used low frequency terahertz pulse, and we detect the polarization rotation. Then we observed that Hall conductivity appears in a positive value and negative value, depending on the left and circular polarized light. So this is the observation of the light-induced anomalous Hall effect in the three-dimensional Dirac semimetals. Now we examined the microscopic picture and look for the topological phase transition by light. So this is a summary. So we have investigated the frequency conversion in Dirac semimetals, and by now we are investigating the ultrafast broadband response function in the multiple frequency, and it can be utilized for the study of the clock engineering. So that's all. Thank you for your attention. Can you hear me?
Yeah, I do hear you. Thank you very much for presentation. Very interesting stuff. Few questions myself, but first let's ask people asking questions. Please raise your hand with the questions, or just turn on.
Can I ask
Yes.
a question?
Yes,
Please.
Michael.
It's a very nice talk, just a very trivial question. So if you tune your excitation frequency away from the 30 terahertz, what do you really see?
So sorry, how can I?
If you detune your excitation frequency away from this 30 terahertz.
Yeah, we actually we
Did you show this? Maybe I missed it because.
yeah, we tune the we change the pump frequency. Then in this case, the same dispersive spectrum appears at the position of the pump frequency. So
okay.
So it appears always around the pump frequency. Okay.
No, I didn't mean changing the width of the laser, but tuning it to say 35 terahertz.
Sorry.
So if you pump at 40 terahertz or something, does that so the effect really goes away?
Yeah. You mean that what happens if we pump at 40 terahertz?
Exactly. Yeah.
Yes. In this case, the same structure appears at around 40 terahertz.
Okay.
So this dispersive spectrum appears always around the pump frequency.
Okay. Okay. Good.
Yeah.
Thank you.
Okay. Thank you very much.
Okay, Gregor, please.
Hi, thank you for this very interesting talk. I had a question concerning the anomalous Hall effect you showed at the end. It was quite fast, but looks very interesting. I was wondering, so do you see any signatures of a gap, topological gap opening as well?
Actually, so in our materials, in our samples, the Fermi energy is shifted about 50 millielectron volt from the Dirac node. Then in this case, I think even if the gap is open, it cannot appear in our experimental setup. So the gap opening is not observed because of the Fermi energy shift from the Dirac node.
Okay, fine. But anyway, very exciting. I'm excited to read about them soon, hopefully.
Thank you very much.
Thanks.
Lech, please.
I thank you for the really nice talk. I'm sorry my camera isn't on. I wanted to ask, but the same slide, how long is your pump in this setup? Like, does this situation live after the pump, or is it only on during the pump?
So you mean that how long our pump lasts?
Yes, please.
It is very similar to the shape of this this pump probe signals. So
okay.
So now almost many part of this light in this Hall conductivity appears only when the pump light is irradiated on the samples.
Sure.
But now we are very interested in how these signals can survive. So now we need more detailed experiment.
Thank you very much.
And what pump pulse width you have? What pump? What's the duration of the pump impulse?
Sorry. Sorry, I can.
What is the pump pulse? What is the duration of the pump pulse?
Duration of the pump pulse. Yeah, it is around 200 or 300 femtosecond. So it's around 300 femtosecond, I think.
Okay, and the thickness of this layer, what is that?
Yeah, sorry. Sorry,
Yeah, the thickness of the layer on what you're dealing with. The material, the matter layer, the material layer.
Sorry, I couldn't understand.
Well, I'm trying to figure out what is the penetration depth of the
penetration depth of the pump. Yeah,
Yes.
penetration depth of the pump is much longer than our thin film samples.
Okay, so you completely okay.
Yeah, thank you.
Completely exposed that. Okay. Thank you very much. So more questions, please. Gregor, please.
Yes, I have a quick follow-up question concerning that data. So do you see a frequency dependence of the polarization rotation of your terahertz probe?
Yeah, this is very nice question. So now we are very interested. But in this experiment, actually the cadmium telluride has a low frequency phonon. So in this case, so in this experiment, this substrate is not optimized. So now we are planning that we should change the samples. Then so this phonon in cadmium telluride is a problem for the frequency dependence of the probe. Now.
Okay, thank you.
So actually, so this is preliminary data.
Okay, thank you very much.